Landin's knot, the bow is kind of a knot, or easier to untie than a knot. I don't know. It's kind of a weird joke. And yeah, we want to thank Amazon for funding this line of work. Okay, so.
And we want to thank IU for your and William's wonderful education.
Yes, that's true. You should have gone further back. Very true, very true.
You didn't give her any money.
That's true. Well, I don't know, maybe the school might have given me a little scholarship. I can't remember. It's been so far.
And
Anyway.
paid for your half of externals.
Oh yeah, exactly. Thank you, Carla, for okay, so I want to start with a little bit of interaction and encourage you all to interact even more. So if we have a functional, strongly typed language, think STLC. When we add higher order references, so mutable references that can store functions as well as other references, basically any kind of type, we typically refer to as higher order references. So the question here is, if we add such references to STLC, that is usually terminating, is this new language with these higher order references still terminating? Jeremy.
Well, I guess maybe Professor John on that. The answer.
Well, I hope that we would have been allowed to answer.
Yeah, of course. Anyone can answer. And if you don't know, that's okay.
Is it just STLC?
Yeah, it's just that there's no tricks here.
STLC is really weak, so.
Yeah, it is.
References are really strong.
Yeah.
Back patching.
Yeah. But how do you start? Like we can't write an option type to put in
You could put
the.
a bogus lambda.
But
Yes.
what is the? Can you make the bogus lambda have the right type though?
Sure.
This is what this is all about. So these are good questions you asked
Sure.
already.
It's easy to create.
I mean, I suppose if you want
Let's say
just a
you
recursive
want
function
the
on.
Ackermann function. You just need 2 integers and returning an integer.
Yeah, that's.
So
It's
you
just
create a
STLC.
bogus, you
That's
create
not very
the k on integers.
Yeah, that's true.
You
Yeah,
initialize
okay.
that,
So
and
yeah,
then-
you can write.
So yes.
It's not.
Oh no, I mean no, it's
Yes.
not.
Yes, but it's not terminating.
Yes, you could do recursion.
Yes. Okay, so if you didn't know, let's go into why that is. So yeah, if we have something like a STLC, which we know to be terminating, and then we add higher order references, we find that's no longer terminating. So I'll give an example. So this example is commonly, or this idea that now we can encode general recursion, is often referred to as Landin's knot. And Landin introduced this in this very old paper from 1964, if you're wondering for the reference on that. Okay, so for example, we could have an identity function on natural numbers, and I'm just defining this to start off with a dummy value for this reference. And what this reference is going to contain is just a function from nat to nat. And I'm just going to initialize it with ID, because I need something to put into that reference to start off. But now that I have this reference, I can define a new function f. And what f is going to do is it's going to dereference whatever function is in R and apply it to its formal parameter n. Now that we have this function f, which is a function from natural to natural, we have this reference, we can just go ahead and update that reference to contain f. And this is all well typed, right? Because they're just functions from nat to nat. And then later, when we try to apply the function f to some natural, like 0, not 1, sorry, I'm giving you a hard time. We find that we're going to go into the body of f. Well, the body of f is going to dereference R. So we find ourselves back in the same situation, and now we have this non-termination. So is this clear to everybody? Any questions about this? Because we're going to look at this example in a lot of detail, so I want to make sure that's clear. Okay, so I want to kind of look at this example in much more detail, and in particular, I want to draw your attention to this reference R. So originally, the reference R contains just the identity function, right? You can kind of just see it right there. And so at this point in time, we would have a terminating program if we just called f, because then f would just dereference R, find the identity, and everything would be fine and dandy. But of course, this isn't what happens, right? We later update this reference R. And this reference R is a free variable in this function f, right? So we're kind of adding this ability to STLC to update the function's environment. right? So originally in the function's environment, it was this reference R containing the identity function, but now we're later updating the function's environment. And that's really what's causing this non-termination. Do you have some doubts about that?
Well, maybe I'd want to split hairs about what is its environment, right? So
Mhm.
because I would like to split there's the environment, and then there's the heap. And so what's changing is the heap.
Right,
The environment's not really changing. It's still a variable to address in the heap.
right. That's a good point,
But I can imagine you're saying, okay, if you include the heap in this picture, then
Right.
fine, something changed.
Yeah. I think more what I want to bring, like, the point is that, like, we didn't have this ability to update a function's environment like this, whether it be the heap or whatever, in SQLC, so we didn't have this ability at all to do this kind of backpatching, but now we do. And that's really where this non-termination is coming from. Not merely because now references can store functions, but because of this update to the function environment.
So maybe is what you're saying that the issue is that we can close over references. And it's not just that we have higher order references,
Right,
but that references can appear in the three variables of a closure.
right, exactly. So we're actually going
of,
to...
of a closure that can go in a reference.
Right.
Right.
Sure, yeah.
If the references were just in that type, then.
Right.
Right.
So, but, yeah, references in function types include closures, and closures are, can include references.
Right, exactly. So we're going to see that. So now that we know that there's something funky going on with the functions environment, we kind of want to make that more explicit, make it typed, make it explicit, so we can actually see, because like at this point in time, we only have nat to nat. We don't know anything about that function's environment, so let's closure convert it so we can actually reason about its environment. So to make the environment typed and explicit, we usually encode functions as data. So we have closed code paired with its environment. The reason why the code has to be closed is because we want to make sure there isn't any implicit environment going on, so that the environment it's paired with is the real one it has. And so as an example, we have our function from before, which is clearly not closed. It has that free reference R. So the way we close it is we just add an extra parameter to represent R. And we're gonna just do the same thing where we dereference it, and then we'll pair it up with the value. And just to make this more general, we usually encode the environment as a tuple. And so that kind of environment would look something like this. It's kind of uninteresting because it's a tuple with one thing in it, thing R, and then just project out. Okay, so we've seen how to make functions into closures, close code, and pairing it with this environment. So now let's think about the types of these closures. So the usual way we represent the types of closures is using existential types, and they have this form where we have a type variable alpha and then a type A where alpha can appear. So then the types of our closures will look something like this. So if we have a function from A to B, then the type of the closure of A to B is going to have the type of the environment represented by alpha. And then we're going to have our closed code take the environment as an argument, and then finally pair it with a value of this environment. So notice in this case that the environment is completely abstract. We don't know how long it is, we don't know what's in it, and that's why we want to use this kind of existential type to hide that fact. And just to see this more concretely, if you're kind of getting lost in the details of the types, here's how they kind of just match up. So you have this closure from before, we have this extra parameter, which corresponds to this in the type, and then pairing it up with the concrete value here in kind of a red magenta. And finally, we need to actually instantiate the type for alpha. And so we know at this point, well, it's going to be a tuple, and there's a reference with something in it. Okay, so any questions on kind of closure converting and the types of closures? Because this will be important to my next point. I don't know how many people have seen typed closure conversion, but it's pretty common. So let's come back to our example and see it closure converted. There's a lot here. What I really want to just draw your attention to is what's in magenta, is that we have two different closures here. We have ID and F. They have different environments and different types, but despite those differences, they actually have the same closure type, existential type, where we're abstracting over the environment, so these have two different environments, but they have the same type regardless, because they take the same input and create the same output. And in particular, they're the type that the reference expects. Okay, so we knew there was something funky going on with F and its environment, so let's unpack it a little bit to see what type are we actually packaging up for the environment type. So I've kind of unpacked it here. Here I'm repeating F and its type here. Oh, I see, I edited the slides here a little bit, but I guess it doesn't matter too much. Based on the shown discussion. Anyway, so we have, maybe it would be helpful to have the same type. I don't know. We'll see if you guys get confused. Okay, so we have the type of F, which is a closure type, which is this type. I've replaced alpha with A here just to illustrate that it doesn't necessarily have to be alpha here. And here's the type that we're packaging up for the environment of F. And what we're packaging up is a tuple type that contains a reference. But if we look inside that reference, we see that we're packaging up the exact same existential that we're trying to define now. That is that A here is going to be instantiated with a type that contains itself, that it finds itself in. And later, when we update R to contain F, we actually find that we also instantiate the inside of that closure inside that reference, also with itself, kind of this circular way. So really, this update to the function's environment is actually well typed due to this impredicativity that we get. The fact that this type variable is quantifying over the type it finds itself in. Any questions on that? Do people know what impredicativity means? It just means this quantifying over itself. Okay, great. You all are very smart, or too nervous to ask questions, I don't know.
So is this telling us that Landin's not is just Girard's paradox?
Maybe.
That like impredicative, I mean, it's well known that impredicative type systems are let you encode recursion.
Mhm.
System F is impredicative.
Well, yes and no.
Not necessarily.
I mean, you do get, okay, you get recursion, but you don't get general recursion.
Right. Well, no, because you can encode, you can church encode non-strictly positive things, can't you?
I thought system F was terminating.
Yes, and it's
Right.
And it's predicative. I think it just,
Wait,
just
That's true.
Impredicative system F is
terminated.
Yeah.
Mhm.
Yeah.
What do you have to do to get Girard? What do you have to add to get Girard's paradox to work?
Yeah, I mean,
Yeah.
yeah. This is difficult because there are many different axes.
Yeah,
It's
yeah,
not
yeah.
like having or not having.
Yeah, sure.
It's true. Okay.
Yeah, the little,
So, but your main point here is great. It's just that your intermediate language with existential is better is impredicative. So
Right.
You can't sort of live in a weaker intermediate language or something.
Yeah, basically like, at the high level, we only see the function type, so we're not really seeing this impredicativity come through, but as soon as you close the converter, you can see exactly where this non-termination is coming from.
Well, so actually I have a question
Mhm.
about that. So, I mean, so what language are we in right now? Is it, this is some kind of like system F with references or?
This is kind of, this
Yeah.
is just the closure converted SDLC with references, so that, yeah.
Well, but
Yeah,
yeah,
that's
that's
the point. He added existential,
Right.
so that's why he says system F.
Right.
Well, so I mean, I have in mind like you can get existentials from like church encoding and a system F, but whatever, I mean, some kind of, right, we at least need existential types,
Right.
but we're still taking references for granted. Like general
Yes.
references.
General reference.
Right.
Exactly.
Because
Now
then there's
they're
some other
creating
questions,
these
yeah, I don't know if you're going to talk about this or not, but there's some other question of like, and where do you get general references from,
Mhm.
right?
What do you mean, where do you get general references from?
Well, like what kind of domain equation do you need to solve to justify the idea of a heap that can contain like references to closures that close over the
Okay.
same heap? And that's also a kind of like knot twisting exercise.
Yeah, sure.
That is maybe a different kind of knot twisting than this.
Or maybe it's the same kind of knot twisting.
Yeah.
Maybe.
I feel like there's a lot of things related here.
But we have not untied that knot, certainly.
Yes,
We're
yes.
still taking that for granted.
Okay, just to recap, we saw that this non-termination or this recursion is happening because of this update to the function's environment or update to the heap. And then we saw that this update is well typed because after closure conversion, we can see where that impredicativity comes through. Okay, so if this update is well typed due to impredicativity, well then a natural question is, well, can you kind of prevent or rule out Landin is not using predicativity instead? Just cut the knot in half, I guess. If we're going with not metaphors or untie it, I guess that was the title, right? So let's take a look at what that might look like. So, if we wanted to make our existentials predicative instead of impredicative, we would add this kind of kinding system to our types with these type levels. So here we're going to add like an extra annotation to our type variable alpha here for our existentials. We're going to say, you know, we can only instantiate it with types at a certain level I. Oh yeah, nobody ever said anything about that. I wonder if people noticed. Okay, and then the existential type itself is going to be kinded at a level higher. And we're using this double colons for kinding. And so you can kind of see why this prevents impredicativity, because obviously we could never take this same existential and put it in for alpha because these levels don't match up. I and I plus 1. This is how we get rid of
This is like the mathematician's fix to like Tarski's paradox.
Yeah,
I just mean
exactly.
like the hierarchy of sets kind of.
Exactly. So we can kind of see how this is, preventing this kind of self-reference. However, it turns out this prevents a little bit too much. So in particular, it rules out higher order functions, just in general. So we kind of seems like this is ruling out a little bit too much. And so why closures require predictivity? Well, quick example, even more functions. You know, if you're not tired of functions yet, you will be after this talk. So say we have a function g, and it closes over some function f here. And to have everything type check, f, of course, has to have the same nat-to-nat type as g. So they both have the same function type. Well, it turns out, if we closure convert the nat-to-nat type, we're going to get this existential type. And then a few steps later, we find that when we're, packaging up G as a closure, we have to say what its environment contains. It turns out its environment contains F, which is the very same type that G is. So to encode this kind of higher order function, we need actually this impredicativity because we want to be able to instantiate the environment with a similar type to itself. Even though this might not be the same G, right? It's just some other function F, but it has the same type.
So what, are you saying that you can't translate nat, arrow nat into exist alpha colon type I for some fixed I? Or, I mean, why can't, I feel like you didn't argue that you couldn't find some I for every function.
You could probably
different I for every
find
function.
some I, right? But yeah, you could probably find some I, actually. That's a fair assumption. But just for like a simple example like this, it turns out a little bit of impredicativity as a treat is very helpful for just being able to encode these higher order functions. And so really what we want is some sort of predictivity restriction, maybe not on the existentials themselves, is the greater point here, because we want our existentials to still have this impredictivity so we can encode higher order functions, but we want some other predictivity restriction. And in particular, so this leads me to my next point actually, is that we don't want to prevent any kind of self-reference at all, because we can rule out fine terminating higher order functions. We want to prevent, in particular, mutable self-references. So this kind of leads us to, instead of restricting our existentials, we actually restrict our, this is just, that point is related to the first insight there. But what we want to do is actually we want to restrict our references and make them predictive. So the idea here being is, if we have some reference that's storing some type A, it's going to be kinded at a level higher than whatever it stores. And then we can still allow our existentials to still be predictive. We have this whole kinding rule. We're still going to annotate our type variable alpha with the level that it's at, but we're not going to have any restriction on J and K here.
I have a question about when you. Okay, so these are the well-formed rules for existentials. But what about like the pack and unpack rules? Do the levels play a role there or not?
Yeah, that was my next point, right? So how do we actually get this annotation on alpha? Well, we check whatever the witness type is, and we check its kind level, and that gives us.
Okay, so that has to match up.
Yep,
Okay.
exactly. Yeah, great question. Okay, so back to our example. Given this new kind of predicativity on references, references are going to bump the level, the type level of things. Let's go back to our Landin's line example now with these type levels. So we have our usual ID here, we're lighting a lot of details. We have its new type here where it's going to be annotating basically the environment type. We need to now know what level does the environment live in. And so the environment is just an empty tuple because there's nothing in the identity function's environment. So we're just going to say it's type 0. And notice that we're going to have this reference R. We're going to instantiate it with ID, so it needs to have this type. And the kind of that reference type is one level higher, right? Because we have this predictivity restriction in our references. Sometime later, we're going to go ahead and define F. Now F, I've provided its environment here, as a tuple containing a reference in it. So this forces the environment type level to be a one level higher to match up with the kind level there. Yes, that was my point there. And I have a helpful arrow to show that F's environment does indeed contain a reference. So then what we find is that when we try to update the reference R to contain F, it's no longer well typed because these environments no longer are compatible. And in particular, we find that this kind of works in general. So if there was some type level I that we instantiated for ID, then as soon as we put that in a reference, that kind level is going to be bumped up, and that forces the environment type level of F. Any questions on this? Kind of, yeah, getting into the weeds of things. But I want to show you the proof for why a language with only closed functions and these closed order references is terminating. Yes?
It feels like once you dereference something, you must not be able to use it again in some sense. Do you see what I mean? And that therefore you ought to be able to use what you have from this is that the heap is sort of straightforwardly not cyclic.
Mm-hmm.
And therefore you can you ought to be able to use the fact that there's only boundedly far that you can follow references to say something about but there you want to be able to be like, I followed this reference so I don't need it anymore, so I can make the heap smaller and then eventually I'll run out of heap to use.
Yeah, that I think is the idea, but we still have the problem that at this level we have functions, but they're particular functions, right?
Yeah,
And so we need to show that, oh, actually at this point, even though it has functions,
right,
it's still terminated.
right, I agree with that.
So, these proofs about terminating languages are, the ones I've seen are usually done with like logical relations.
Mhm.
So I was kind of wondering if that's coming up in,
Yeah.
in the slides here, or
No, luckily there's no logical relations proof, actually.
and
For
if
this,
not,
this
why
one,
not?
this closed order one is very sneaky, and I did not come up with it, so you'll see
Uh-huh.
how this one works out. It's
Okay.
it's
'Cause, I mean,
everyone got upset when they saw this proof because it's a little sneaky with the closed functions, right?
but it sounds like so you don't have a proof.
But
the
not
whole
for
thing.
this yet. But I want to do, yeah, I think
I mean-
I'll start with logical relations. And
I would
then
think
see.
that if you do like maybe some kind of step indexing
Mhm.
but with the
Mhm.
steps correspond to your levels or something.
Exactly, yeah. So basically what we're doing is we're taking that step indexing work and now we're saying, oh, what if you just had it in source language?
Mm.
Right. And so we're hoping.
Well,
yeah,
it's
a
different. I mean,
Yeah.
usually the step indexing is like with respect to actual steps of computation.
Right.
But this
Yes.
is sort of a different
Yes.
thing.
Yeah, it's very weird. Very, very weird. So we're going to see how the logical relation works out.
Cool.
Wish me luck.
Good luck.
Yeah, that's the first step is doing syntactic. Connor has a paper from 2018, I want to say, that's about a monad for full ground references. So it's not references that can contain functions, but it's references that can contain other references, so cyclic. And they ended up kind of having a similar thing in their semantics with levels. I don't quite understand it because it's category theory, but Ohad is teaching me, so hopefully we can kind of see. And he seems to see some sort of connection. Oh, like with these levels, you know, should extend it one step further and include functions. So hopefully that will also work out. We'll see. Okay, so I wanted to show you this very sneaky. Oh yes.
Just before you read next slide, remind me
Yes.
what closed order references are.
Yes, yes. So we have a language that only has closed functions, and it's also going to contain references, higher order references, but since our functions are still closed, I call them closed order references to kind of distinguish them from functions with any kind of environment.
Okay, so it's like general references, but in
Yes.
a language that sucks.
Yes,
Okay.
exactly.
Right.
Yes, generally. Yeah, I wanted to call them general references, but I think people more heard it as higher order references. I'm not sure, but yeah. Okay. So the way that we prove this language, this language that sucks with general references, basically this language with closed functions and general references, how we prove that it's terminating is we convert it to a language with a ground store through defunctionalization. So defunctionalization is usually used to convert higher order functions to first order functions. Here we're using it to convert closed functions to data. So the way that we do that is, say you have two functions here, and they're obviously closed, right? They only refer to their formal parameter and some base data. And I'm just going to say, okay, well, I know I have two functions of this particular type, so I'm going to convert the first one to 1 and the second one to 2. And you might be like, how is this a function at all? Well, and you know, we took so much time to convert our functions and closures and thought about the environment a lot. Well, there is no environment here, so we don't actually have to worry about it at all. We can just go ahead and convert it to the numbers 1 and 2. And then they kind of work as labels, right? So we basically converting our closed functions to just labels, and we say, okay, when I actually want to apply a function, I'm just going to look up based on its label and perform the operation that I want. Okay, so how does this actually work out in the types? So if we have the conversion over reference types is just going to be kind of the same as you would expect. We just convert the type inside. But when we convert function types, well, it turns out we just converted them to numbers, particularly just a finite type of type n, where n is the number of functions with that particular type. So now, there are clearly no more functions than references. They only contain finite types. There's no more functions at all, actually, in this language. And so this insight in this proof came from Max Neo. So those big thanks to him for kind of this insight about closing the environment of a function to kind of give back termination.
Is the fact that like multiple different functions are going to have the same number of, or is that like the different types might have the same number of functions with that type? Is that an issue? Like the hash collision?
The idea of like, then like when you apply them, you would probably have to make it more specific based on the type then. So this would be like dfun app end to end, and then one.
Okay.
So then, yeah.
Just another
It's based on the
reference.
type and the number of that type.
Like references a little bit easier, and yeah, another key. And
Yeah. Exactly. That's a good question. Okay, so very CP proof to get back termination. Okay, so just to reiterate overall of like how we want to prove that this language is terminating, we say, okay, the store 0 is roughly equivalent to a ground store, maybe through some, probably through some kind of, we probably need a little bit more work with logical relation, but we want to say it's roughly equivalent to a ground store, probably through some sort of kind of trick, maybe through defunctionalization, that could work. But we still have to worry about the environments as a problem. But yeah. And then we just proceed kind of, like Sam said, you say you kind of like run out of heap, you're kind of just following the lines along the way. And this is all just work in progress at the current moment, but we have a lot of intuition as to why it might be terminating, which is why we pursued this in the first place. Okay, so just to summarize, we took a very deep dive into a single example of Landin's not, found out there was some secret impredicativity, or not very much exposed in the function type. And then we were like, well, what kind of predicativity restriction could we come up with? We thought, what about on references instead of on the closures themselves? Which led to this kind of stratified store, which we hope to prove that this is terminating language soon. And thank you all very much. Yes?
Is there, so this is obviously like an interesting sort of theoretical question, which is like, is there a language that sort of gives you general references but not the full sort of Turing completeness?
Mm-hmm.
But is there also like a practical like motivation here? Like, are there reasons why you might want a language like that?
Yeah, so this is all coming up out of work of a dependent type preserving compiler. So, you know, in the compilation process, you want to allocate things on the heap. But since this is dependent type theory, you want to keep your language terminating because that keeps your type checking terminating. And so we're wondering, is there a way to kind of combine general references and like a terminating language in a safe way so that we can retain that termination? So in the larger goal, it's sort of like mixing dependent types and references.
So this is, you need it in the implementation of the compiler or in the code generation? Or I'm sorry, I missed.
Oh, no,
that
no,
one
no,
by
no,
fast, so-
yeah, it's for the, we want to design a compiler that preserves the dependent types all the way down to
Okay.
assembly.
Okay.
And since in dependent types, your types rely on terms, you end up having to basically evaluate terms. And we want to make sure that those terms are still terminating because we want our type checking to still be terminating. And then as we go through the compilation process, we need to allocate things on the heap. And so we're saying, is there a way to mix a dependent
I guess
type
that's
theory
the
with
step that
references?
you said as you go through the compilation process, you need to allocate things on the heap.
Mhm.
Like, are you talking about the compilers? The compile time? The heap of the compiler at compile time? Or are you talking about is changing to a
Yeah,
the
it's
language, the code that you're generating
Yes.
is using a heap?
Yes, exactly.
Okay, the later. Okay.
And so we want to we want to preserve the types from the higher level IR to the IR that allocates things on the heap. We want to make sure that's type preserving.
Okay.
But the language in the IR with the heap is reasoning about the heap, right? And so we need more reasoning about the heap in our type system.
Okay. Okay, I get it.
But if you're going all the way to like assembly or something, like a dependently typed assembly, is that like what the?
I mean, that's the overall goal.
Sure, but then that will have non-termination and dependent types. Yeah, so at some point you have to like give up
Or maybe,
Yes.
I mean, or maybe not.
Or maybe not.
Maybe you have a terminating x86,
Yeah,
dependent x86.
yeah.
Sure.
Who knows?
Okay.
I mean, that would be the goal, but also, there's an argument to be said that, if you're starting in a source language, like already terminating, and then in a type preserving way, you kind of stay in this terminating fragment. That could be an argument to be said that it's still terminating by the time you get down to it, even though there might not be terminating things. There's that argument also.
That's right.
You could just go untyped and
Yeah.
live all free.
Yeah. Yeah, who's gonna think about all these types, You just go to Python.
So one thing I wonder about is whether you can, so like you should have to prove termination here by encoding away the functions.
Mm-hmm.
But I wonder if you can encode away the references. And like in general, it's hard to sort of encode away references when they can be circular, because like you need to encode them into something else that's circular.
Right.
But like these references are not circular,
Mhm.
and so could you just encode the whole thing into like a big series of finite maps?
Right.
And
Yeah.
then you're just in a language you're just like writing a program in the state monad where your
Right.
state is
Exactly.
a big finite map, and then your program is sort of obviously terminating
Right.
because where would the non-termination come from?
Yes. Yeah, I mean, definitely, so logical relations can be hard, especially with this like weird, this isn't the steps, this is like this
Yeah.
is the index of the heap. And so, yeah, I mean, we're definitely looking into like the idea of like, oh, can we just encode this as like a really weird state monad, and then kind of like at the bottom level we say, well, we know that in the environment there's nothing, so we can basically consider it ground or something. Yeah, I could definitely imagine something like that, and that might be easier than logical relations.
Yeah, because
I feel like
there's no-
there's got to be like multi-prong approach to modeling
Yeah,
this.
there's no, like you can encode that as a collection of finite functions, and then eventually map to like these weird sort of ground functions.
Yes.
Ground values, and then you're just programming in the STLC again.
Yeah.
Yeah. Or like in whatever system you want.
Yeah.
And then
Yeah,
that's
absolutely.
obviously terminating. So if you just have a compiler from
I mean, that's
your language to that weird store passing,
Yes.
then it would have to be terminated.
Yes. That would be a much more obvious proof as well, as opposed to maybe category theory. But
So does this prevent all cycles in the heap?
yeah, so
Because it
that's a common question I get is like, well, doesn't this like restrict a lot of other programs? And it's like, yeah, probably does. So there's maybe
Maybe
that's
that's
next
a-
step
maybe
is
that's
like
another-
cyclic kind of data
Yeah.
structures. How do you encode those and make sure they have?
Is there a way to somehow allow cyclic structures but not cyclic
Yeah.
function
Yes.
closure structures?
Yeah, exactly. Yeah, that's the next step. And see what kind of like restriction we can come up with there. Because I think currently probably restricting some cyclic structures. But we still just want to basically stratify the functions. Yeah, bro.
I don't know if you've thought about this or not, but I see that references induce ordering on the kinds, and your goal is to use this techniques to compile dependently typed programs toward IR that uses heap. So, and in dependently typed languages, you have universe levels. So I was wondering if this kind of a hierarchy is orthogonal to universe levels.
No, I mean, I think it's related, for
Okay.
sure. And it would probably then, maybe there's an argument to be said, well, actually we want just a purely predicative dependent type theory. And then so we can have this kind of predictive restriction. maybe they'll end up being those kinds of restrictions. But we haven't looked into extending this to
Right.
kind of types yet.
Okay.
You mentioned in the talk that by putting the kind index on the function types, it's actually too strong. Like the restriction is too strong. Do you have like an example which is rejected in that design, but is accepted in your current design?
You mean
Yeah,
with,
the one with the F and the G.
yeah, you mean with the predicativity restriction on existentials? Oh god,
yeah.
so many slides. Oh boy, oh boy.
Because I think you mentioned the design
Yeah,
where
yeah.
we can put the kinds on function types, for example.
The kinds
yeah.
on the function types? Was it this example where why closures need this predicativity, or on the
this,
later?
yeah, this one I think, yeah.
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 Yeah. So basically, if we had this restriction on saying, okay, now our existentials are predicative, so it's
Yeah.
one level higher
Right.
than what it quantifies over, we essentially rule out functions like this that close over functions of the same type. You could probably, like Carlos said, you could probably like send the levels up high enough where you could encode this.
Mhm.
But in general, this is what's nice about encoding closures as existentials, is because, well, we have higher order functions, and so we can just say, oh, in G's environment, which is represented using alpha,
Mhm.
we're going to say we're going to have F's type, which is the same existential. Make sense?
Yeah.
I answered.
So you still can't write self-referential functions, right?
Yeah, the idea is like, how can we prevent self-referential references? We want the restriction on references instead, because references are what's going to allow us to update to ourselves, but we don't have any way of writing recursive functions in SDLC. So this function is not self-referential, F is some other function. But this would prevent this kind of higher order function, rather than preventing the ability to self-update.
I mean, it would be nice to write like factorial. Something.
Yeah, it would be. SDLC is,
Well, you can, I mean, there's lots of things you can add
yeah.
to STLC that preserve termination,
Mm-hmm.
like fold on the naturals.
Right.
And then you can write factor.
That's true.
Uh,
But for now, just like writing higher order functions would have been, this would have been too strong of a restriction, which led us to the restriction on references instead.
I wonder if you can add or move the restriction to closures. So like,
Yeah, it's sort of
This
like
is
that.
the
I guess I'm not so
restriction is-
sure that this, did this
Did
restriction?
you throw away this restriction too quickly,
Yeah, maybe.
Right, because I think that if you have a terminating language with higher order functions, I think that, you can pick like for every term, you know how many kind of times the closure gets instantiated or something. You can basically pick a high enough universe level where, so it would be that there exists an I such that there exists alpha type I.
Right.
Right. So it's not like uniform because, you can, if I say 100, you can find a term that will need 101, but there will always be some number that will
Right.
work for any term.
Yeah, maybe you could, I mean, maybe we did throw away this restriction on closures instead too quickly. That could be an avenue to explore, is like, don't mess with the references, they're the same as normal, but do have a predicativity restriction on this, and then see kind of what that language might look like.
yes. And I mean, you could, like, in general in system F, like, predicativity, like, it's this combination of closures and existentials and references that, well, or it's this combination of existentials and references, and
Yeah, it's
Uh,
actually
you could make your references predicative, you could make your existentials predicative. I wonder if you could make the combination predicative.
right.
Uh,
we were kind of exploring that design space as well, as like, this has a certain level, but then once it's put in a reference, it has a different level, and sort of like restricting it.
that like when you go
There's
from
different universe levels for closures and.
yeah, that you have to have some level
Yep.
change when you put an in between like the binder and the reference for your existentials.
Yes, exactly. Yeah, we were thinking about that as well, like having basically two different hierarchies. But we found it kind of like weird, and we found that this was
Yeah, I mean,
simple
this
enough
is,
to
this is-
seem to do it.
This
you
is
know?
nice and simple, and
Yeah.
like seems clearly to ensure termination. I mean, Nigel approving it.
Yeah.
Um,
I mean, I love disclaiming stuff and not proving good stuff. Someone's gonna cut that out of the video. Oh, no. But yeah, I mean, yeah, there's definitely. I feel like there is definitely space here between these.
Or the, right, so the version you've got rules out any cycles on the heap.
Mm-hmm.
But it's sort of only cycles that go through functions that really give you the non-termination. Because you have some way of getting like, having it be like a go-to.
Yes.
And getting the control flow involved.
Yeah.
Mm-hmm, mm-hmm.
And the existentials by themselves sort of don't do that either.
Yes.
But there sort of has to be a function type involved somewhere.
Mm-hmm.
And so that makes me wonder that, you know, I don't know, that you have some sort of thing that would really want to track, some more complicated type system that tracks, or kinding system that really pays attention to function types
Mhm.
and existentials,
Yeah.
Yeah, I mean-
references or something crazy
Yeah.
like
I mean,
that.
one thing is there's the translation from function types to existential types. And you could imagine putting, and that is a
Have to use this equation, you know, that the doomsday clock ticks down by one, right? And so it
Every
seems,
time you do like an unfold.
yeah, exactly, right.
Of the recursive.
But-
type or whatever.
So when you have like general references and closures and all this stuff, you end up with some sort of equation that's like, well, you know, the heap equals location arrow, you know, whatever value, but a value can be a closure, which blah, blah, blah heap. And so
Yes,
then you
yeah,
also
that's
end up with
exactly
a
what
D equals D or D type situation.
That's exactly
Right.
Yeah. That's
So, and that's one place where you can use step indexed
right.
logical relations to approximate, you know, a solution to the domain equation.
Right.
So it kind of feels to me like what you're doing is you're putting the subscript in a different place, but it might be that it kind of works for the same reason
Right.
as it works if you put it in the other place.
Yes.
So it might be that the kind of whatever usual step indexed argument for termination, you know, would kind of work here, just like in a
Well, I think
It's a different
part of the tricky thing of trying to adapt prior work is that a lot of times the step index logical relations for like Amal
right.
did were not for terminating languages.
Exactly. Yeah.
Um,
Yeah, that's-
but I think that could be still fine, because, I mean, it's sort of like, you know, with your logical relation, you need to be able to define that relation in Agda or whatever, right?
Mhm.
And so to have a well-defined thing, you know, like the easiest thing is like, oh, I do recursion on type, my type index.
Mhm.
And those things, you know, are well-founded, so that's all well and good.
Mhm.
But then here, if you're like, oh, if I get, and then with step indexing, it's like, oh, there's another, now you're doing your recursion on the step index. And so you get it well-defined, and that should work fine here too. Where was I going with this? I guess, but I think you can, there's a huge amount of freedom in terms of when you define your logical relation, what you then you define the big E, the fancy E
Yes.
part of your logical relation, right? That says what does it mean for expressions? And then you get to say like what the behavior of the program has to be at a particular type, right? And when they're doing non-terminating ones, they usually it's sort of like this partial correctness kind of thing, where you allow it to not terminate. But if you're doing like STLC, then you say, oh no, it goes to a value, period.
Yeah.
And who knows, maybe you could just do that in your
Yeah.
logical relation
Yeah.
for your big E.
Yeah, sorry, I should have, that's a very important point that I forgot to say, which is, it's like you are living in the step index model of a non-terminating language, but you're restricting the source language so that the step indexed pseudo model is a genuine model of your language. That's the difference, right?
With the terminating.
Well, right, because, I mean,
I
because
see,
step
I see,
index
yes.
logical relations are not actually models of, like, non-terminating, like, they're used not because they're models, but because they're good enough, they're close enough to models
Right.
that you can pick a big enough number that you can prove,
Right.
partial
Right.
correctness. But
I see.
if you live in the model, then everything does terminate.
Right.
Right, and you're going backwards and saying, I have a theory that is, whose genuine model is step index.
Yes. Yeah. We were definitely, very much inspired by this.
Yeah, if you're gonna try to do the logical relations in AGDA by chance, then
Yeah.
I would either try what Max is doing, which is using Garden Cubicle for that, or if that scares you or it doesn't work out, I have a library for doing step indexed. It's basically a step index logic on top of AGDA.
Oh.
Now, it has its own complications,
Okay.
but it lets you, it's sort of like the LSLR logic from Amal. It sort of encodes that.
Is that,
in AGDA?
Is that on your website? I
Yeah,
guess? I'll be able to find it.
There's a
Okay.
GitHub
Or you can send
repo
it to
for
me.
it and some blog posts. And
Oh, okay, perfect.
I
I'll
have
read
a
this.
draft of paper I can give you.
Yeah, that would be great. Yeah, that would be super interesting. Yeah, definitely want to go into where I go at. So, be like, I wrote 14,000 lines of that. Hopefully not.
I also think going back to what Carla was saying about like how you get this domain equation that can't be solved, that when you write down the equations for a model of a language with general references, but it's mutually recursive
Yep.
and not directly recursive the way D
Yep.
D or V is.
Yep.
And
Yeah,
basically
literally
all the
write it-
different-
I've thought about it so
all
much,
the
I can
different
literally write it down.
suggestions that we are made about where you could put the predicativity basically correspond to what if we put the index on this arrow,
Yep.
or what if
Yeah.
we put the index on this arrow, or what if we put the index on this arrow, and
What is it like?
or what if we put the index on the combination of these arrows, and you get the you get different yeah.
Right, but it might be easier to just see, are these equivalent or not, like in
Yes.
systems of equations.
Right, right.
Not that.
Yes.
I'll run it. Hold on.
Yes.
And then usually, so people, to avoid this non-termination, right, they might say, okay, well then we'll just have like a particular store type, which will be like base,
Yes.
and then it doesn't, or something like that.
Yeah.
Or just foul.
Yeah.
So,
Yeah.
Having fun, neat stuff.
wow. Well, thank you all. This is great. Oh, there's a chat. Oh, I'm so sorry.
Oh no, he just left.
Okay.
Yeah.
Okay.
No questions.
Okay, good.
It's like that.